Okay, and welcome back. So we're going to derive the 1D kinematic equations of motion when acceleration is constant. These you've seen in your book. They've been derived same way for longest time. So we're going to just kind of review the way to derive the equations. There's a couple of concepts that you should know about, like if you take the derivative of the position function, you'll get the velocity. If you take the derivative of that, you'll get the acceleration. If you haven't taken calculus, don't worry. These are just concepts that if you know about these things, or at least these are the things you will see, they kind of help motivate the derivations. But for the most part, all you got to know is that there's a relationship between the velocity and the position, not just with the equation, but in a much deeper sense. So that's kind of beyond the scope of this tutorial, but just something I'd want to mention. So look forward to calculus. Okay, so what we're going to do is we're going to start with the acceleration. And you know that to be delta V over delta T, right? Okay, so what does this mean? Well, we can look at this as a slope, right? So if you were to take, I don't know, let's just say, for instance, a line, right? And I guess we can make like a little X and Y axes. And we'll let this be the velocity versus time axes. Now, the reason why I chose that, again, you'll see a little bit later. I'll try to mention it, but the motivation for this can come from calculus, or if you just mess around with these equations enough, you'll find that this is really probably the best way to go about deriving these equations. So with that said, this is your initial time, time 1, time 2. I guess we could call this T initial and T final. In fact, that's pretty much what we'll be doing from now on, initials and finals. And so this will be V final, and this will be V initial. Okay, so there's essentially like a little triangle here. If you look at this, this essentially is your delta V, and down here is your delta T. Okay, so what we can do is look at this and say, well, A is nothing more than the slope of this, okay? So what we can do is take our acceleration. This is actually, when we write A is equal to delta V over delta T, we're talking about the average velocity. The average acceleration. However, just for notation, I'm just going to call it acceleration, okay? And this will be V final minus V initial over delta T. And if we multiply by delta T on both sides, we get A delta T is equal to V final minus V initial. Okay, and we can rewrite this equation as V final is equal to V initial plus A delta T. Okay, and this would be our first equation. So one thing to note about this is that this could be considered like our y equals, this A is a slope, right? So essentially that's like our m, and delta t is like our x, and this v sub I is like a b, right? And what does that look like? Y is equal to mx plus b. If you were a calculus student, or if you're taking it with this class, with the physics class, this is helpful to just note that you're dealing with a line here. And I'll make reference to this again, but just note that this is really nothing more than a line, okay? Also, another thing, note that you have V final, V initial, so that's two variables in this equation, okay? For right now, these are unknowns, okay? And A and T, right? So note that you have 4 unknowns. Okay. So from this right here, I guess we can look at this. This graph again. And this time, since we right now have an equation dealing with the final velocity, if we take a look at this, in calculus, you're actually doing something called integration, okay? integration, you learn about integration, and really what it is basically you're getting the area under a curve. So this line here is, for the most part, it's a type of curve. It's just a line, but we're actually interested in the area under the curve. And in calculus, you learn that the area under the curve is the amount of distance when you're dealing with a velocity function. So if you take a look at the area underneath this curve and you calculate it, that'll tell you how far you've actually gone, okay? So what we're going to do is take a look at the area under the curve, and we're going to let that be our distance, and we're just going to call that delta x, or our displacement, okay? And basically all that is really just the area of the triangle plus the area of the rectangle, right? That's basically all it is. So what we're going to do is, well, the area of the triangle would be 1/2 times the base times the height. So the base is delta t, and the height is v final minus v initial. So it would be 1/2 times delta t times v final minus v initial, right? And the area of the rectangle is going to be v sub I delta t, right? Because the height is v sub I minus 0, which is v sub I, and the base is delta t, okay? So that's going to be, we're going to add, let me move this over just a little bit. Okay, that's better. So that's v sub I times delta t. All right, so what we're going to do is, I guess, just simplify this a little bit. So we're going to get a 1/2 delta t v sub final minus 1/2 delta t times v sub initial plus v sub I delta t. And we can take the negative 1/2 delta t v sub I plus the v sub I delta t, add those together, and we'll get 1/2 delta t v sub f plus 1/2 delta t v sub I. We can then factor out the 1/2 and the delta t and write it this way. 1/2 v sub f plus v sub I delta t. And this would be our displacement. So this would be our second equation, okay? And one thing to notice is that you've got an x, you've got a v sub f, v sub I, so that's 1, 2, 3, and a delta t, so that's 4 unknowns. So again, you've got 4 unknowns. So that's twice it's happened, so it seems like there's a trend here. So you've got 4 unknowns in the first equation, and you've got 4 unknowns in the second equation, okay? So let's clean things up a little bit here and kind of rearrange these equations and put them off to the side. Okay, that's better. All right, so what we're going to do now is we're going to trade off the v sub final from the first equation, and we're going to try to relate delta x, basically the displacement, to the acceleration. And so we do that by substituting in, well, I guess I should name these. This would be equation 1, this would be equation 2. So you'd actually take the v sub f and substitute that into the second equation. So let's go ahead and do that. So we'll start with equation number 2, and we'll substitute in the v sub f from equation 1 into equation 2. All right, so v sub f is going to be this v sub I plus a delta t. So it's going to be some stuff plus another v sub I, and that's going to be times a delta t. Okay, so you see how I did that. I took the delta t, put that on the outside. The 1/2 is on the outside as well. And the brackets essentially are these parentheses here. This v sub I is this v sub I, and this v sub f actually goes inside of here, but I'm going to write this as v sub I plus a delta t. And then I simplify. So I could just add the v sub i's together. So I get 2 v sub I plus a delta t times delta t. And distribute the 1/2 delta t into here. So I'll just write this again anyway, just so that way you can see it. I'm actually putting the delta t in the front, and then I'm going to multiply that. I mean, it's just basic algebra. I'm going to multiply it. I'll distribute it into the binomial here. Okay, so okay, so the 1/2 delta t times the 2 v sub I just becomes v sub I delta t. And the 1/2 delta t times the a delta t becomes 1/2 a delta t squared. So this is your displacement when you have acceleration. So when you know the acceleration. So notice here you've got x v sub I, it's one unknown, two unknowns, the time, which is also located inside of here, so that's three unknowns, and the a. So again, you've got four unknowns with this one as well. Okay, four unknowns. So if you've taken calculus, you might recognize this as being like, think of it like a y is equal to, this v sub I would be like a b, right? This delta t would be like an x, and the 1/2 a would be like 1/2 a, and this delta t would be like an x squared. So just if you don't mind, I'll just erase that right there. And essentially, you've got y is equal to ax squared plus bx. So that is just a polynomial. And that's a quadratic equation, which means that you've got some kind of picture of a parabola, essentially, right? But this is the position function. So this tells you like where something is at a certain time given an initial velocity and an acceleration. But in the beginning, we derived this equation here, equation number 1. Actually, let me just go ahead and call this, set this in stone. This is your third equation right here. And this equation is a quadratic equation. However, the first equation is a linear equation. So I'm just going to say this now. When you take calculus, you'll find that the position function, which is essentially something that looks like this equation here, if you differentiate it, you will get the velocity function. So that means the position differentiated gives you the velocity, and the velocity differentiated gives you the acceleration. Again, that's beyond the scope of this tutorial, but it's just something to think about. For those that have taken calculus, if you haven't, don't worry about it. You'll see it. Trust me, you will see it. It'll make complete sense. Again, this is just looking ahead, so hopefully this kind of motivates you to be interested in calculus in the future. Okay, so that gives us our third equation, and I'll need some more space again, so let's move things around a little bit. Okay, and that's equation number 3. Okay, so for the last one, we want to get rid of the time. So we want to get an equation that doesn't involve time. Why would we want to do something like that? Okay, messing around with these equations enough, you'll find that you can pretty much get the results you need. Again, when acceleration is constant, you can get the results you're looking for because you've only got 4 unknowns every single time. So you're dealing with essentially a total of 5 variables, right? Or 5 unknowns, right? So you've got the v sub I, v sub f, time, position, acceleration. I mean, so that's 1, 2, 3, 4, 5, right? So that means you can have 4 unknowns without the time. So in order to do that, what we can do is we can start with equation number 1 and just isolate the time, and then we're going to substitute that one into 2, right? Because notice this equation here has the x, v sub f, v sub I, so that's 1, 2, 3, and delta t. Well, we can get rid of the delta t, and we're going to have v sub f and v sub I, as well as the a, all go inside of this equation, and that'll give us 4 unknowns. So let's try that out. So we'll start with equation 1, and we're going to move the v sub I over to the other side. So we get v sub, I'll just write the equation again. V sub f is equal to v sub I plus a delta t. We're going to isolate the delta t so that we get v sub f minus v sub I is equal to delta t. And this side is all over a. So we're going to take this and we're going to plug it into 2. So we'll get equation 2, and we'll write this down again, equal to 1/2 times v sub f plus v sub I. Now instead of the delta t, we're gonna plug this into it. Okay, so I'm gonna put that in parentheses, and so this will be v sub f minus v sub I, and that's all over a. Well, these are all factors, so I could just write the a right next to the 2. So I'd have 1 over 2a, but then I could just multiply 2a on both sides so that I end up with 2a delta x is equal to v sub f plus v sub I times v sub f minus v sub I. And if you recognize here, these two binomials, they look like a plus b times a minus b, and that's equal to the difference of squares, right? So this is just v sub f quantity squared minus v sub I quantity squared. No need to distribute or FOIL this out. It's just an automatic thing. I mean, you can do that if you want, but it's just faster knowing how to recognizing it. It's just faster recognizing it. Okay, so what do we have here? We got acceleration, we got displacement, so that's 2 unknowns, v sub f, v sub I. Again, we got another 4 unknowns. So in every single case, we've got 4 unknowns. And this equation is the last equation, and this one is the time-independent equation. So that means there is no time in it. Okay, now something that, I don't know, it occurred to me when I looked at these equations. This would be equation number 4. Well, one thing I notice about these equations is that they all have 4 unknowns, right? And we're dealing with a total of 5 unknowns with these kinematic equations. So if we take the variables, well, I mean, if we take the unknowns and put them in a tabular form, meaning we create a table of these variables, we'll get something interesting. So we have equation 1, equation 2, equation 3, equation 4, and I've got v sub I, got a delta t, I got a v sub f, I've got an a, and I've got a delta x. Well, for equation 1, I've got a v sub I, so I got a v sub I there. I've also got a delta t. I've got a v sub f, and I've got an a. I've got an acceleration. In the second equation, I've got also a v sub I, also got a delta t, and I've got a v sub f, but I don't have an acceleration. However, I do have a delta x. In equation number 3, I've also got a v sub I, and I've got a delta t, but I don't have a v sub f. However, I do have an acceleration, and I do have a displacement. And in the fourth equation, I have a v sub I again, but I have no time. However, I do have a v sub f, and I've got an acceleration, and I do have a displacement. So what's interesting is that looking at these equations here, I guess if you look at it this way, this is just to help you remember in case you are not allowed to use a sheet or a cheat sheet for your exam and you have to try to generate these equations. You may not remember them. This might be kind of helpful, I guess, in helping you check to see if you have the right equations. Notice that in equations 3 and 4, you're dealing with squares, right? So you just got to remember there's a delta t squared in equation 3. In equation 4, the velocities are squared. So just remember equations 3 and 4 have squares in them, so I guess you could remember squares down below. Okay, well, I hope you found this helpful. And if you're taking a calculus class now, or if you've taken it already, then you'll see the relationships between the linear equations and the parabolic equation. Maybe I should say one other thing. The velocities that you're dealing with here, the velocity function with respect to time, and the position or displacement with respect to time, the displacement is your delta x, right? And your velocity is your, velocity function, basically. So you may see something that written like x of t, okay? And you may see something like v of t. So when you take the derivative of this position function, which is x of t, you'll get the velocity function. And when you take the derivative of the velocity function, you get the acceleration function. It's all with respect to time. Again, if you haven't taken calc, don't even worry about it. It's just when you go take the class and you revisit this, you'll see how this makes sense. So essentially, if you just start from here, you'll get to this function, you get to this one. And then going back the other way is something called integration, but I'm not even going to touch upon that right now. So, well, anyway, I hope you found this helpful. And as always, good luck with your homework and tests in the future. And thank you for watching.